Hi. This is not a complicated assignment, but being a capstone project of this course, with a limited time available to carry it out, I thought that it might be useful to offer some design hints to simplify your work. This is the first of two presentations with that purpose. After watching this presentation, I hope that you will be able to explain how the CPU of a storage program computer works and to describe the role of each block in its architecture. Likewise, I hope that you will be able to draw the ASMD chart for each instruction and to add instructions of your own to the VHDL design file. The presentation comprises three parts, starting with the data path architecture, then the ASMD chart, and finally the corresponding Vivado works. Let's start by the data path architecture. This slide revisits the minimal CPU architecture that has been shown in an earlier presentation. You may recall that each of these blocks has to be present, or otherwise it wouldn't be possible to execute a program stored in memory. The instruction register holds the instruction code while it is being executed. The program counter generates the memory addresses. The data register enables us to carry out some form of data operations. And the instruction decoder and execution control unit is responsible for coordinating the operation of all the other blocks. So the first three blocks make up the data path, and the instruction decoder is the control path of this FSMD. Let's move on to designing a small set of general instructions for this minimal architecture. This slide shows the ASMD chart for a jump instruction. The destination address is fetched from the memory position that follows the instruction code. Notice that the first state carries out operations that will be needed for any other instruction as well. And then the following state, called AL1, checks if the instruction code corresponds to jump. If that is the case, then the program counter is loaded with the destination address fetched from memory. This slide shows the ASMD chart for an instruction that loads the data register from memory. Please pause the video for a moment and try to explain it in your own words, considering the explanations that were presented in the previous case. In this case, we have a halt instruction that is meant to stop the CPU from continuing to fetch instruction codes from memory. It shouldn't be difficult to understand and explain how it works. These three examples will be sufficient for now. So this slide shows how the three partial charts can be put together to define the complete ASMD chart of the CPU. Pause the video for a moment and make sure that you understand how the complete chart works. We are now ready to move on to Vivado. What I am showing you here is the first part of the complete VHDL design file, where the entity section was hidden for reasons of space. You may again pause the video to check the initial part of the architecture section, comprising the signal declarations and the state register block. In the second part, you see the VHDL blocks describing the next state and output sections. It shouldn't be difficult to understand this code, but again, please consider pausing the video to check what is done in each state and to compare the code with the complete ASMD chart that was shown earlier. Notice that this block of code starts with a set of default signal assignments for the next state and the next value of the program counter, the instruction register, and the data register. It is important to include these default assignments because we won't have to repeat them anymore throughout the state descriptions that follow. All we have to do is to provide different assignments if the operations needed are different from what was defined as default. And here's an example of the simulation results that I obtained with my own implementation. Notice that in this case we are simulating the execution of the jump instruction. Please make sure that you understand the sequence of events shown in this simulation section. And that's it for now. Thanks for your attention.